So 11 o'clock, first Sunday of the month, and time for chai and wine. And before I formally introduce today's speaker, there is just please speak. Because we have a single microphone for streaming.
Oh, I
so
see.
This will pick up.
You can use it.
No.
You can. I want you to use it and then hand it over to
Okay.
me.
All right. All right. So before I formally introduce our today's speaker, there is just a small announcement that 28th of Feb, that's the last Saturday of this month, is the National Science Day, and TIFR will be open for the visits. So details of that can be found on our webpage. So do visit our webpage and do visit TIFR on 28th of Feb. Now let me introduce today's speaker. So our today's speaker is Professor Girish Kulkarni. He is very much from the state of Maharashtra. He studied in Pune initially, did his PhD at HRI, then went on to the Western world for his postdocs. And in 2018, he chose to come back and join Department of Theoretical Physics at TIFR. And now he is engaged in his research, which is all about looking back where it all started. We really don't know, right? So now, without further ado, over to Professor Girish Kulkarni.
Thank you. Thanks, Ulas. Okay. Oh, केलं होतं ना आपण? Is that better? No?
Yeah, you're good.
There you go. It's my first time giving a talk in a theater. There are wigs and empty wine bottles just behind this track. I was taking selfies there with those items just now. It's really nice to be here, and I should start by thanking Ulhas and Arnab and TIFR for the invitation to give this talk. I have been in Mumbai for about 7 years, a bit more than 7 years, but I haven't had a chance to give a chai and why talk yet. So it's really nice to be doing so today. The idea behind today's talk is I wanted to introduce all of you to 3 what I think are exciting problems and puzzles about our universe, particularly connected with the first billion years of our universe. But what I also want to convey is not just the puzzles, but I want to give you a sense of what we here in Mumbai are trying to do to solve these puzzles. Often I find that that's not something that's conveyed as readily as the puzzles themselves. So I do hope that by the end of this talk, you have a sense of what people like me in TIFR in Mumbai are trying to do to solve some of these exciting problems about our universe. So now, if you go to a place where there is very little light pollution, probably as far away from Mumbai as you can, typically you see a sky that is full of stars. I don't know how many of you have had the privilege of seeing a night sky that looks like this. We don't have that kind of a sky in Mumbai, unfortunately. I also grew up in a big city, not in Mumbai, but also in a big city. And so I actually distinctly remember when I first saw a starry night. I was about 10, and I got out of a bus in a remote spot outside the city where I lived. And I was just stunned by how the night sky looked. And so we are familiar with at least the idea that there is such a thing as a night sky full of stars, right? And some of us may have seen it. What we do not appreciate as much or as readily is what exactly does this represent, this night sky? It represents, of course, a small view from here, from this planet called Earth, of the entire universe. And often we don't pause to appreciate what that really means. And so what allows one to do that, what allows one to pause and appreciate the size and scale of what we see when we see the starry night sky, are these modern extraordinary telescopes. So if you take one of these powerful telescopes that are in existence today, and this is one of the best telescope that is operating at the moment, this is an American telescope called the James Webb Telescope. What you find is a very different night sky. What you find is something like this. Okay, what is this? This is one of the deepest photographs taken using the James Webb Space Telescope. And this is a remarkable photo in many ways, and it really brings home the enormity of what we see when we look at the night sky. The first thing to note about this photograph is almost every point on this photo is not a star but a galaxy. Itself a combination of billion or a trillion stars and planets and gas and so forth. The second remarkable thing is that this thing, which is occupying a small area of the screen in front of you, is actually a really tiny part of the night sky. How tiny? This is actually a third of the limb of the moon. So the moon is a very small portion of the sky, about 30 square arc minutes. This is about 8 square arc minutes. So just that tiny sliver of the night sky has these many galaxies distributed in it. But the third enormous thing is how big is the volume. And the volume here is trillions of kilometers by trillions of kilometers by trillions of kilometers across. So that little sliver of the sky contains this vast space, which contains this enormous number of galaxies, each of which contains this ginormous number of stars and so forth. This is the enormity of the universe that lies behind that beautiful starry night when we look at the sky above. Okay. And what cosmology tries to do is try to operate at that enormous scales. So the cosmology is a weird branch of science, is a weird branch of astronomy, which says what we will do is we will try to study the whole universe as one physical system. This gigantic system of trillions of kilometers across, that's going to be what we study. And that's called cosmology. And this is something not everyone thinks about daily. Not everyone is like me, who earns their salary by doing cosmology. And so it's really important to get this across. So what are some of the big length scales that we are familiar with? I'm sure many of you know kilometers. Mumbai is very good for that. And the next jump in astronomy from kilometers is a length unit called the astronomical unit. Do people know what astronomical unit is? It's roughly the distance between the sun and the earth, the average distance between the sun and the earth. And that's about 10 to the 8 kilometers, which is 100 million kilometers, right? That's pretty big, as you might agree. But that's nothing for cosmology. We need bigger units. So cosmology, one of the favorite units in cosmology is the light year, which also many of you might be familiar with. That's the distance that light travels in a year. That's about 1,000 astronomical units, 1,000 times the sun Earth distance. But even that's nothing compared to that photo that I showed, compared to the volume that I showed. And we need even bigger units. And actually, a unit that we routinely use in cosmology is a length unit called megaparsec, which perhaps not that many of you might be familiar with. And a megaparsec is about 1,000,000 light years. Okay. And a megaparsec is a small distance when you do cosmological calculations. Okay. And so cosmology is astronomy on 100 megaparsec to 1 to 10 gigaparsec scales. So you might say, well, what's the point of this? Why are we studying cosmology? What is it to gain if we go at these very large scales? Is there anything special, or is this just a race to become bigger and bigger? And so one of the great physicists produced by India, Subramanian Chandrasekhar, many of you might have heard his name. I hope all of you have heard his name. Actually pondered on this question, that why is it that we should study largest scales in the universe? He asked it for astronomy, which itself studies very large scales. So his comments are doubly valid for cosmology, which even within astronomy tries to study extraordinarily large scales. And uh, he says, granted that physical science as a whole is worth pursuing, but what is the particular case for astronomy? What is the particular case for cosmology? And his answer is, my own answer has been this. Nature exhibits different patterns at different levels, and the patterns of the largest scales are those of astronomy. It's a remarkably interesting answer. The point is, the world around us appears very differently at different scales. At the scales of us humans, kind of meter scales, we are familiar with the world. Things we can move by pushing and pulling. We know the concepts of heat, hotness, and coolness. We know things like things dropping when we leave them aside on planet Earth. We know gravity. But when we go to extremely small scales of atomic length scales, and length scales of an electron or a proton, we know that things don't work like that. Completely different laws of physics work. And Chandrasekhar said, well, something similar must happen when we go to very large scales. And therefore, it is important that we study these larger scales in cosmology. These are the reasons that drives us to study the universe at these very, very large scales. And so what cosmologists do is that they try to ask questions of the following kind. They ask, well, how and when did the universe form? Did the universe form at all, or has it been always like this? What is the age of the universe? If it did form, when did it form? What does the universe contain? Does the universe, is it dynamic? Does it change, or is it mostly just the same all the time? If it does change, how is it changing? What is the universe going to look like in the future? So as soon as you go to these grandest length scales and consider this whole universe as one physical system, you can ask these questions that you will ask to any other physical system, from a bunch of liquid in a beaker or a bit of gas in this room, for instance. So this is the job of a cosmologist. And what's remarkable is that just 100 years ago, if you asked these questions about the universe, you would be considered a crackpot. Okay? People thought that there is no way mankind can learn anything about these grandest of length scales. In fact, Ernest Rutherford, one of the great physicists, many of you may know him from your atomic physics lectures, etc. He was the head of the department, of the physics department in the University of Cambridge in the UK. And he said this, I'm not making this up, he really did say this. He said, don't let me catch anyone talking about the universe. And indeed, if you look at the thinking that went under the name of cosmology 100 years ago, around 1920s, it was really crackpotty. Okay, people had no clue what they were talking about. What's remarkable, however, is that since then, cosmology is completely transformed. In the 100 years since Rutherford, today cosmology is one of the most precise and exact sub-branches of physics. Most detailed sub-branches of astronomy. And in fact, there are properties of the universe that we understand really more precisely than the properties of the gas in this room, for instance. Okay, so it's completely changed from just 100 years. And indeed, Rutherford had a point. There is no reason for evolution to equip our brains to study these 10 gigaparsec length scale. We don't need to understand the universe to survive here on Earth, I think. Right? But somehow, in these 100 years, we have managed to figure out a lot. And so what I want to do in the next few minutes is give you a sense of what we have learned so far about the universe, and then point you to what is still a bit puzzling, what doesn't make sense in the universe. Okay? Now, one of the interesting things I find about cosmology is that as a field of study, it's remarkably similar to archaeology. You know, archaeology is about digging up the past, and cosmology is exactly like that. And I really find that really interesting, that parallel between these two fields. So for example, if you show the photo of your favorite city to an archaeologist and you say, I want to understand what was there where I live, what was there where today Mumbai is 1,000 years ago, 10,000 years ago. What an archaeologist is going to do is going to dig up a patch of Mumbai. If they can find a patch in Mumbai to dig up, they'll probably dig the patch up. And then they're going to probably going to go layer by layer deeper into this little patch. And the idea would be that they will reconstruct the history of this landmass where Mumbai today stands. Maybe at some depth, they will find a bit of ruins of old buildings, and they will study these, and they will try to make claims that so-and-so people lived here, this is what they did, this is the kind of buildings in which they lived, right? We all have seen photos of places like Harappa, Mohenjo-daro, and Lothal. This is exactly what archaeologists do. What's absolutely remarkable is this is exactly what a cosmologist does. And the reason a cosmologist can do this is because the universe comes equipped with a time machine. And the idea is, because the speed of light is constant, because it's finite, the farther away you look from Earth, the backwards in time you are looking. So the universe is a patch for an archaeologist to do this digging, and the digging tool is really simple. It's just light. And we do this all the time when we look at the night sky. When we look at the moon, we are actually looking at the moon as it was a second ago. We are already looking a bit into the past, right? Many of us probably know this. When we look at the sun, we are looking at the sun as it was 8 minutes ago, already a bit in the past. And so on. For example, Mars is about 12 light minutes away from us. So when you're seeing Mars, it's actually Mars as it was 12 minutes ago. Similarly, when you look at these far away galaxies scattered across the universe, you're actually seeing the universe as it was billions of years ago. And that's the archaeological element in it. So all you have to do is to go and look at this night sky, and this is your archaeologist's patch. And you use light to peel away layers of history from this night sky. That is all that a cosmologist does, day and night. Okay? And the more layers you peel, the more interesting information you learn about the universe. The first interesting information you learn about the universe is it's just full of galaxies. Galaxies are like the atoms for a cosmologist, just as somebody who studies gas or liquids considers atoms as the fundamental blocks of these materials. For a cosmologist, the fundamental block that creates their system of study is galaxies. And the universe is just full of it. These galaxies look like they have varieties of shapes and colors. And in fact, there are so many galaxies now that people can construct robotic telescopes which can go and find millions upon millions upon millions of galaxies on their own. Okay? And one of the best robotic telescopes at the moment has conducted an observation of this kind. These observations are called surveys. And these are just automated telescopes looking at the night sky and identifying galaxies and doing these surveys. One of these greatest surveys going on at the moment is a survey called DESI, which is a strange word to say in India, but it is dark. It is the full form is Dark Energy Science Instrument, and this is what it came up with. This is the map, our latest map of the universe. We are at the center of this map, and every point here is a galaxy. Okay. You can see the color is just a false color artifact having to do with how the instrument identified galaxies at various distances. But the range of distance here spans about 12 billion years in time. Okay, so this is almost close to the Big Bang here, these farthest objects. And we are here, and the whole of the universe is just full of these galaxies. What's remarkable, however, is if you zoom into this map, you find that although these galaxies are distributed randomly, they're not quite random. They have some structure. And this structure looks like this. It's known as the cosmic web. I hope you will agree that it's a good term because it does look like a cobweb. It has these filaments, it has these voids, holes in it. It has some structure. It's not like a uniform distribution of sand grains on a beach, for example, or it doesn't have any special geometric patterns like circles or squares. It has a very specific structure which looks very similar to a cobweb. And so this is a remarkable finding from the days of Rutherford, where a cosmologist was just a crackpot, to finding out observationally by means of telescopes that the universe contains these trillions of galaxies which have this specific structure is, I think you will agree with me, a gigantic improvement in our knowledge about the world. In fact, not just that, it has turned out that not only can we see that beautiful cosmic web, we can now describe it mathematically. We actually understand it quantitatively. This has resulted in a theory of our universe, and that theory is called lambda CDM model. That's the Greek letter lambda there. It is also often called the Big Bang model, but that's a derogatory word towards us cosmologists. You should never use it. The correct word is lambda CDM model. And the lambda CDM model is a beautiful theory in physics which describes that cosmic web. It explains our universe. So from 100 years ago, from Rutherford's time when we had no clue about what the universe even contains, we now not only know what it contains, we have a beautiful quantitative mathematical theory of describing it and explaining it, called the lambda CDM model, one of the grandest achievements of humanity. And the lambda CDM model has 3 pieces. I'm just going to mention them because it's just so interesting that we should all be aware of it, even though studying it mathematically might require a PhD. This is just absolutely thrilling. The first piece is that the lambda CDM model tells us how the universe looks like. It says that at very large scales, if you ignore those little spaces between the galaxies, the universe feels like a smooth surface. Okay, you remember the map that I showed? If you just zoom out a bit, you can't really make out that it's made up of these tiny dots. It's just a smooth distribution of points. So the lambda CDM says, yes, that is what the universe looks like. As soon as it is a smooth surface, it says that this smooth surface is described by an equation called the FLRW metric. It's not important for us here to understand what it means, but FLRW metric is a mathematical object that describes smooth surfaces. What's remarkable is that as soon as you have something like an FLRW metric, lambda CDM model says that the universe fits Einstein's theory of gravity, which is given by this. Quite amazing. The universe is a solution of an equation that a man wrote down in 2025. Just as Rutherford was making that comment, this equation was being invented. And then lambda CDM model says that smooth surface has properties. It is flat. It expands. This is where the expansion of the universe comes from. The universe is constantly expanding. Things are moving away from each other. But what is remarkable is that lambda CDM model also says that the universe has a finite age. More than 13.8 billion years ago, lambda CDM says that the universe did not exist, which is a remarkable fact. This is what is known as the Big Bang. Okay, so this is the first part of the lambda CDM model. Again, you'll agree with me that it's really remarkable that we can find all this out about the universe at these 10 gigaparsec scales. But there is a second part to the lambda CDM model. The second part is, what does the universe contain? And lambda CDM says, if you want the universe to look like what it looks like, if you want the universe to have this cosmic web-like structure, then it must contain 4 things. What are these 4 things? Something that we call ordinary matter. This is just the elements on the periodic table that we study in chemistry. But it also has something that is not on the periodic table, namely something called dark matter. It must have that. Otherwise, lambda CDM says you won't get a cosmic web-like structure. It also has something else called dark energy. Again, we don't quite know what this is, except for a mathematical term in the lambda CDM theory. Again, it says you need dark energy if you must have the universe that looks like what it looks like. And finally, it must have light. Okay, it must have photons interacting with these 3 constituents. Of this, what we can see in laboratory is just ordinary matter. Okay, of that, almost everything in the universe is hydrogen. The universe is just a play of hydrogen. There is a bit of helium, a really small amount of lithium, but the universe has just that. All the rest is produced by stars. So all the atoms of which you and I are made of, they actually were produced by stars. If stars didn't exist, we wouldn't exist at all. That's the second part of the lambda CDM model. And the third part of the lambda CDM model is actually, for me, the most thrilling of it, which is that it says not only does the universe contain these things, not only is the universe smooth and flat and described by Einstein's theory, it has another remarkable property that on that smooth, flat surface, there are really tiny ripples, okay? They are literally ripples like that on the surface of a water, of a lake or a sea. Lambda CDM model doesn't know where these ripples come from. It doesn't tell us that. We have no clue who created these ripples, what created it. But it says they exist. These ripples have to exist. And as soon as you let the theory, allow the theory to have these ripples, it says, well, as soon as you have these ripples, they are going to grow because of gravity. And when we take our best understanding of physics and evolve these ripples, they produce exactly the cosmic web that these telescopes today see. Okay, and this is an example of that calculation. Okay, this is now a very straightforward calculation that students do when they learn cosmology. It's that simple. That you have these ripples. Again, nobody knows where these ripples come from. If you can find out, you will get a Nobel Prize. But if you allow for us to have those ripples, they grow. And doesn't this look exactly like that zoomed in sliver that I showed you? Okay, this is not uniform distribution of sand. This is not a smooth, regular geometric distribution like a crystal. this is a very interesting cosmic web, a cobweb-like distribution. And if you mathematically compare these distributions with the data, you find that the agreement is remarkable. Agreement is very, very uh, accurate indeed. In fact, this whole story has now got 8 people Nobel Prizes. Okay, so this whole edifice of the lambda CDM model have the first Nobel Prize on the lambda CDM model was given in 1971, and the latest was just a few years ago in 2019. And these 8 individuals have slowly built over these this whole story of these 3 ingredients that I told you about. Of course, with help from many people who could not get the Nobel Prize. And now, if that's the beautiful edifice of lambda CDM model that I am calling the greatest achievement of mankind, and if so much has been learned about the universe in the 100 years since Rutherford, I now need to tell you what I am doing in cosmology, right? I need to tell you what these 3 mysteries are that we mentioned in the title of my talk today. And so to do that, I want to go back to that parallel between archaeology and cosmology, because there is a remarkable difference between the two fields that I want to use to explain to you those mysteries. Okay? So here is a simple parallel, which is, let's actually follow the archaeologist as he or she goes deeper in the ground, or a cosmologist as he or she goes deeper in the sky. And there is going to be a very simple pattern to what they find. For example, at the very surface layer, a cosmologist will just see a normal city where people still live, an archaeologist, I mean. And equivalently, for a cosmologist, it would be a present universe with lots of data, with galaxies and stars and these surveys of the kind that I'm saying. This is the surface layer, right? Once you go a bit deeper, we know that the archaeologist will start seeing some ruins, maybe some broken buildings of not that long ago. But maybe, so there will still be some structure. And the equivalent for a cosmologist would be some nearby galaxies and some emergence of a cosmic web type structure. If we follow them further, the cosmologist, maybe deeper still in the ground, will see some fainter ruins now. They are a bit more broken and they are not as well preserved. And for a cosmologist, equivalently, we will now see earlier galaxies, slightly older galaxies. We call them the higher redshift universe. And then there will be a bit more uncertainty. There will be debates on where this galaxy is located because the data quality is pretty bad. So the pattern is clear. As the archaeologist goes deeper, the data quality, the quality of knowledge, the confidence in the knowledge degrades. Similarly, as the cosmologist goes deeper in the sky or backwards in time, the data quality and the confidence in the knowledge degrades. If they keep going further, I'm sure the archaeologist will find some bones and tools or something like that. I'm not an archaeologist. I'm not sure what exactly people find at that depth, but one can imagine that there must be some layer before the buildings where they find these tools and bones. The corresponding equivalent of the cosmologist is some very faint galaxies or galaxies that you only identify indirectly via their spectral lines or something. And if you still go further, then of course both investigators are going to hit blackness, right? At some very great depth, the archaeologist will say there is nothing here. There is no sign of human civilization. I have gone deep enough that there are no buildings, no bones, no tools, nothing. And similarly, a cosmologist will say that I have now gone so far into the night sky, I have gone so far backwards in time that there is really nothing to be seen there, no observational access. I'm very close to the Big Bang. And indeed, really close to the Big Bang. Nobody has probed the universe yet. We agree with this. And so if I try to make a diagram of our understanding of the universe or of that archaeological field, it will look something like that. That today, when the universe is 13.8 billion years, our understanding of the universe is really, really good. Lots of information, very accurate measurements, very good understanding. But as we go backwards in time, slowly the amount of information and the confidence in our understanding will degrade. It turns out, for a variety of reasons, not all having to do with technology, that somehow near about the billion year marks, we hit some sort of a watershed. Somehow about a billion year mark, we really hit that place where there are not even bones and tools. There is hardly any data available. Okay. But that's not the end of the story. There is one bizarre twist on the cosmologist's work. which is not there in the archaeologist's side. Which is, imagine that for the archaeologists now, beyond this last layers of bones and tools, they keep digging and suddenly they find a layer where suddenly there is a fully preserved city. Beautiful, neat, posh, modern, just no people, but the city is there exactly as if somebody lived there just a minute ago. Okay? And then again, beyond that city, there is nothing. How bizarre that would be, right? But exactly the same thing happens for a cosmologist. Somehow, this need not have been. This is a completely fortuitous, non-fundamental, accidental, fortunate fact about our universe that somehow, when we go deeper into the universe, into the night sky, at some point, we hit something called the CMB. And that CMB is an extraordinarily rich and detailed snapshot of the universe at that one point, as if a day in the universe was preserved when the universe was young. And then again, beyond the CMB, there is literally nothing. We have no observational evidence. So in fact, this is how the CMB looks like. This is an observation from a European space telescope called the Planck telescope. And I'm just showing a small part of the full map that they have. This is a extraordinarily detailed map. This is literally how the universe looked like when it was about 100,000 years old. Okay, these are those tiny ripples that we have in lambda CDM model. And as a result of this, the universe, the cosmology story is slightly different from the archaeology story. The cosmology story now is that we have a lot of information today. The information and our confidence in our knowledge about the universe degrades. At some point, it goes away. But then, suddenly, at some one point, which is about 100,000 years, that one point suddenly we recover a lot of confidence and knowledge. It's really bizarre, right? It's really odd. And this need not have been the case at all. It's easy to imagine a universe where this couldn't have happened, but we happen to be living in a universe where this does happen. What this does is it creates a very interesting gap in our knowledge where we have to now reconcile our understanding of the universe here with our understanding of the universe here. Okay? So this is what I do in my research group. My job is, my hope is, in 20 years, I will come and give a talk in Prithvi Theatre where then there won't be a gap here. We would have filled it. Okay? But what I'm going to do now is to try and explain to you how we fill this gap. But more importantly, I want to tell you 3 remarkable mysteries about these gaps, which is what people like me get excited about and work on this gap. Before I go to the mysteries, however, I just want to pass on one important concept to all of you, which will be very useful when we discuss these mysteries. And this concept is the idea of spectroscopy. Okay? Some of you may already know it, but others might not. Spectroscopy is this idea which really turns astronomy into physics. Okay? Spectroscopy was discovered in the 19th century, and that's where astrophysics became physics. Astronomy became physics. And the idea behind spectroscopy is it's a technique in astronomy. Spectroscopy is used in other areas of work as well, including medicine, etc. But in astronomy, it's a beautiful technique to see faint things that are otherwise very hard to see. So I don't know how many of you know this, what is shown here. What is shown here is a photo of the limb of our sun. Okay, but what you can see here is this tiny black dot. That black dot is the planet Mercury. And I don't know if you know, planet Mercury is really hard to see because it's very close to the sun, so you can only see it in the morning or in the evening, and it's very hard to see, but it's really, really easy to see when it crosses the sun. In fact, this is the only way I have seen Mercury. I've never seen Mercury in the evening or morning sky. It's just really, really hard, and our skies are now so polluted that you can't see near the horizon at all. But when you have the Mercury doing this, what is called occultation, when it comes in front of something bright, namely here the sun, then it's very easy. You can spend an hour looking at this, no problem. Okay, very comfortably seen indeed. This is the essential idea behind spectroscopy. All of us know what a spectrum is. When you pass light through something like a prism, the light disperses, and depending on the frequency of the light, which we also refer to as color, it will actually land at a different point. So in other words, if I put a prism on a telescope, the image of these millions and trillions of galaxies will each disperse and produce these kind of a multicolored image. And you get something like this. I don't know how many of you can recognize this, but this is the spectrum of the sun. Okay, this is a remarkable spectrum. And This is a lot of history associated with this image, which I won't be able to go, except maybe I'll tell you one quick thing, which is the most detailed continuous observations of the sun are present at only 2 points on the planet. One is France and the other is India. So the observatory in Bangalore, which is now in Kodaikanal, which started in Fort St. George in Chennai, moved around as the politics of the country evolved and has converged to Kodaikanal, is the longest observations of this type of spectrum of the sun. But the idea is you can get a familiar looking spectrum which has light going from red to green to blue. But what is beautiful is that you can see these gaps in the spectrum, right? These little black marks where no light is coming to you. What's happening here is exactly like that mercury occulting the sun. Something faint is deleting those colors from reaching you. Something faint is intervening between the source of these photons and you to eat away some of the light. Okay? And these something is just the atoms in the sun. And the reason these are these sharp lines is because atoms turn out to have this bizarre property that they only absorb light of specific colors. Again, it need not have been so, but it does happen to be so that atoms respond to specific light. It was as if mercury responded to certain frequency only. As if when I look at the sun at color 1 or frequency 1 or wavelength 1, I don't see any mercury here. I change my color to color 2, and then now I suddenly see mercury blocking the sun, and for a third color, the mercury is gone. This is exactly how, this is of course not how mercury behaves. Mercury blocks everything coming from the sun, but this is not how atoms behave. Atoms literally eat away only specific frequencies coming from the source behind them. And why does this happen is a very deep and long story in physics. That simple question has led to the development of quantum mechanics. I have, of course, no time to talk about that here, but there are a few aspects of it that are important for what I'm going to tell you, so I'll just mention them here. First is atoms only interact with light at special frequencies. Okay, if light coming onto an atom, shining on an atom, does not have any of these special frequencies, that light will pass through as if the atom doesn't even exist. But as soon as the light has these colors, these frequencies, these wavelengths, something weird will happen. Okay, the photons will be absorbed. And the reason this happens is because atoms turn out to have specific energy state. Again, really bizarre. You need to really understand quantum mechanics to know why it might be the case. If I drop a ball here in front of me, the ball falls down smoothly and it has all possible energies as it goes down. But if I imagine what an atom does when the atom moves into its energy spectrum, it actually goes step by step by step. There is no energy state in between. Okay, and so atoms must be, apart from the fact that the frequency of the light must have special values, atoms must have special energy states to interact with those values. For example, if the atoms are here, they will absorb the special frequency 1, but they will not absorb special frequency 2. Because when the light of special frequency 1 comes in, these atoms will absorb that light and change their energy state. So you need to have two things happen. The light must have a special frequency, and the atoms must be in the right place to actually deal with that. If either of these conditions are gone, that light has no business interacting with the atom. It will not even notice that the atoms exist there. So if both of those conditions are met, then something beautiful happens. You have a spectrum that you can plot like this. Astronomers usually plot the spectrum like this, with the brightness or the flux of the light on the vertical axis and the color or frequency or wavelength on the horizontal axis. And you will see some light everywhere except at one point where things will be absorbed, because that was a special frequency and because the atoms between us and the source happened to be in the right state, right energy state to actually interact and absorb that light. Okay, this is spectroscopy. This is what I need you to remember for me to tell you about the 3 mysteries of the first billion years. But before I move that, there are 2 amazing things you can do using this idea in cosmology. The first thing is, using this, you can actually count atoms far away in the universe and actually measure their temperature. So this simple, stupid idea of atoms coming between a bright source and you and absorbing light away turns out that it acts as a extraordinarily sensitive thermometer. So it's actually more sensitive than the thermometer we use to measure our fever or something. Okay, you literally can count atoms billions and trillions of light years away and measure their temperatures extremely, extremely accurately. Because what happens is that as soon as those atoms have finite temperature, they start moving around, jiggling, as if they have some random motion. And as soon as they have that Doppler effect, this idea of trains sounding differently when they approach you versus they recede from you, exactly the same thing happens between the atom and the photon. The atom starts seeing different photons to be at the right frequency because the photon is like a train approaching the atom. And as a result, the atom starts now responding to slightly different frequencies than that special frequency. And therefore, that little absorption line becomes a broad absorption line. And how broad is that? It is as broad as the temperature of the gas will allow us to. This makes spectroscopy a thermometer. So if the gas is hotter, the line will be broader. So all we have to do is put a nice prism in our telescope and you can measure the temperature of the universe wherever you go. But that's not it. There is another remarkable thing, which happens only in cosmological spectroscopy, which is that the universe is expanding. So all the time this light is traveling, the universe is expanding. So the frequency and the color of the light is changing because these photons are getting stretched. And as a result, different photons are becoming special frequency 1 as they travel between us and between the source and us. And so something like this happens. This is the same absorption line occurring at different points as this bunch of light is traveling from that source across these billions of light years to us. And what it's doing is at each point, it is creating this beautiful barcode of absorption lines. This is all just one transition, but it's occurring at different points as the universe expands. And this now allows me to trace everything between me and the source at extreme resolution. Now you know everything for me to tell you what those three mysteries are and what those three problems are. Okay, so we have this amazing tool called spectroscopy, which we can use to measure temperature, and we can use it to measure the structure of anything between us and the source of the light. So what are these three puzzles, three mysteries? So the first mystery is really easy to state. We have never seen a universe which doesn't have galaxies. I made this whole story about how we can go back in time layer by layer. There has to be a layer, lambda CDM says, where no galaxies should be there, but we haven't seen. Galaxies never appear to form, they always exist. So how can that be? Okay, that's the first mystery. This image I showed, this has millions of galaxies in it. This also has some of the oldest galaxies, the earliest galaxies that mankind has seen. In fact, I gave a version of this talk some months back. And at that point, this was the oldest galaxy. What's remarkable is that this galaxy itself is also a pretty well-formed galaxy. It's like an extended object with gas and stars. It's a very bad quality image because this is very far at the limit of the sensitivity of the telescope, but it's a galaxy. We routinely see stars getting formed or destroying. Why don't we see a galaxy being born? Why is there never a watershed beyond which there are no galaxies? Why is even the farthest galaxy looking like that? In fact, when I agreed to Ullas to give this talk, I was preparing this talk. While I was preparing, a new galaxy has been discovered, which is now the farthest galaxy. Okay, this was literally, I think, reported 30th of January, which is 2 days ago. Okay, now when this galaxy, again, it looks like a reasonably well-formed galaxy, again a bad quality picture, but this costs about $2 billion, so it's we will take this, I think. And it has structure in it. It has gas. You can take a spectrum of it and study which elements this galaxy contains, how many stars it has, and so forth. In fact, even the people who reported these galaxies are amazed. They call it a cosmic miracle, a remarkable luminous galaxy at redshift, which means time, confirmed with JWST. Even they are stunned that this galaxy exists. These are the same people who created that beautiful photo of the zoomed in sky. So the first question is really why? Why do these galaxies exist and how did they happen? Lambda CDM has no answer to that. We want to find that answer. Indeed, one of the goals behind the James Webb Space Telescope was actually to find this answer. Was the primary goal. But now the concern is JWST just seems to find more and more galaxies farther and farther out. What if somehow that layer is just out of reach of this telescope? Maybe you need a super JWST to actually reach that stage. What if that is the case? Maybe then we will never be able to make progress on this problem. Indeed, that is a very real possibility. And so some of us, including me, have come up with a totally different line of attack. And this line of attack is not original with me. The idea first came in a paper which almost nobody reads. It has some 10 or 11 citations from the 1970s from the Soviet Union. And these guys said there is something else that those first galaxies will do. So maybe you actually don't have to try to find the galaxies at all. You try to look at their effect on the universe. And so what do? They said, okay, look at the CMB. You know the CMB, you know how to look at it. It is accessible to your telescope. Let's actually just look at the CMB instead of trying to find these galaxies. And what they said was that just as these galaxies form, something interesting will happen to the CMB. And now why? We can understand that because they identified something using the principle of spectroscopy. They said, well, you know this familiar hydrogen atom, like any atom, it has these energy scales, energy states. Two of these energy states have a separation which correspond to the special frequency or special wavelength of 21 centimeter. Okay? There's nothing special about this. There are many, many energy states. They said, okay, look at this particular pair of energy states. This pair has separation of 21 centimeter. Now, if the separation is 21 centimeter, whenever a 21 centimeter photon comes, hydrogen is going to absorb it. But only if the hydrogen atoms are in the right state. Remember, it has to have two conditions to be satisfied. The frequency should be right and the atoms should be in the right state. And so what these two Soviet writers said was that normally in the universe, all hydrogen atoms are in the upper state of these two. Because they are in the upper state, whenever a 21 centimeter photon comes, they simply don't interact with it. But the point is, they argued, as soon as galaxies form, the galaxies produce, for the first time in the history of the universe, ultraviolet light. It simply doesn't exist before the galaxies. And they showed, using statistical physics, that as soon as you have ultraviolet light can pull all the hydrogen back to the lower state. As soon as hydrogen atoms come down to the lower state, they will start interacting with 21 centimeter. So now all I have to do is CMB is my ready-made backlight from the period when the universe was 100,000 years old, and it's going to pass through all the universe between me here and that time. And at any point, as soon as galaxies form, all the hydrogen atoms come down and that 21 centimeter is gone. And again, because the universe is expanding, this will happen at a particular spot in the spectrum. And they said, just find this spot and you will have your job. In fact, these are some of the calculations that we have done in the group. This red curve shows the number of atoms that are on the bottom layer of that energy state. And in this plot, galaxies form at around that time. And you can see as soon as galaxies form, the atoms are all pulled down on the lower energy state. In fact, the most detailed calculation of this was done by a student in my group called Shikhar Mittal, who is now a postdoctoral researcher in the UK. And here he calculated for the first time a very detailed picture of how these ultraviolet photons from these first galaxies go and pull these atoms down to the lower energy state. Is this just an idle curiosity? No. There was this beautiful telescope called EDGES in Australia. This was built by a small American group. This really made a sensational claim in 2018 that they have seen it. They have actually seen that spot where the atoms all come crashing down to the lower energy state, and you see this absorption. This was their figure. Unfortunately, there was another group that was doing a similar experiment. This was from India. This is a group from Bangalore, and they have this is their telescope. These radio telescopes look very, very weird. They don't look as romantic as an optical telescope with a grand aperture. But actually, this has a much bigger aperture. This is seeing the whole sky. And they put their telescope on a lake in Karnataka. And they didn't see anything. So what's going on? Are the Soviets wrong? Are these telescopes having any issues? What's going on? And so people like me are trying to do these calculations to see if the Soviet prediction is correct. But we are not sitting with that. These are the telescopes that me and my friends have constructed. This is our own telescope. It is called REACH, and it is operating as we speak from the deserts of South Africa, where it's a beautiful part near the South African-Namibian border. And it's taking measurements to see if we will find this. Okay? That's the first mystery, where did the galaxies form? A second mystery, again about that gap in the diagram of the cosmological evolution, is about weird objects called supermassive black holes. Almost everyone amongst you must have heard black holes. Not everyone knows what supermassive black holes are. And still, fewer probably wonder where they come from. So I need to explain what these things are. So the story goes back to 1960s when this remarkable astronomer who is now sadly passed away called Martin Schmidt, he used to work at Caltech, a university in America, and he observed using the Hale telescope this small patch of the sky in the Virgo constellation. Most of these are stars in our Milky Way galaxy, and he was observing them, characterizing them, getting their spectra and so forth, the normal work of an astronomer. And he observed this one star there, which was unlike any other star. Firstly, its spectrum looked very weird. Again, you see in the image, it looks exactly like a star. This is the star that we draw when we learn drawing in class when we are in primary school, right? Stereotypical star. But as soon as you take a spectrum, it looks completely different from any star. In fact, from its spectrum, it also was possible from Martin Schmidt to infer that it is actually billions of kilometers away. And it's also receding. It's actually moving at enormous speed, 16% of the speed of light. In fact, it was such a sensational discovery that year Martin Schmidt was on the Time magazine's cover. Okay, it's actually feels like a sci-fi cover. It reminds me of the age where science was this romantic, right? I think the internet has ruined science a bit because everyone has information in our pockets now. What's amazing was that Martin Schmidt found this one object, which he named 3C273. But now we know millions of these objects, actually. And we now know that what these star-like objects, which are not stars, they are called quasars, which is a short form of quasi-stars. They're almost stars, but not quite. So these quasars, we now know, are actually really, really massive black holes. So you must have heard news of people detecting lots of black holes these days using gravitational waves. These black holes have mass of about the same as our sun. But these supermassive black holes have masses of about 1 billion suns. And what happens when you have such a huge black hole, this is just a painting, not a photo, is it attracts a lot of gas around it. And because of the intense gravity of this black hole, the gas swirls around this black hole and heats up. It heats up to such a high temperature that gas starts emitting tons of light. That light is what Martin Schmidt saw as a star. And because this whole thing is a very compact system, this is about the smaller than our solar system, it really appears as a star, a point object, not like a galaxy extended. In fact, now we know that every galaxy in the universe has this supermassive black hole sitting at the center. Our own galaxy has one. If you look at the Sagittarius constellation, you will see a supermassive black hole rise on the sky and set. It has about 1 billion suns mass. In fact, if you had X-ray vision, if you, instead of seeing normal light, you saw X-rays, night sky would be unaffected by light pollution, and it will be full of supermassive black holes, studded with supermassive black holes. In fact, this is an image of the night, small patch of the night sky. Every object here is a billion to trillion solar mass black hole, accreting this gas, which is emitting tons of X-rays. In fact, I have spent 5 years of my career just counting how many supermassive black holes exist. It turns out counting is very complicated in astronomy. It takes 5 years to count something. In fact, here is a remarkable example. This is a photo taken again using the James Webb Space Telescope. But on top of that photo, you also see this purple cloudy stuff. This is another photo taken using the Chandra X-ray telescope, superimposed on the James Webb Space Telescope photo. And if you zoom into this, you find this little object. It has a name called UHZ1, which is actually the farthest known supermassive black hole. Okay, this also has some, we'll see, I think 10 to the 10 solar mass. The problem is this thing exists when the universe was about 300 million years old. So the point is, these objects also always seem to exist. We never see anything that has mass between about 10 to the 6, 10 to the 7 solar masses and 1 solar masses. Somehow these appear to come pre-made. Where do these supermassive black holes come from? That's the second mystery. And because the farthest objects are again around that billion-year mark, this mystery is also taking place in that gap, in that black region between the CMB and the limits of our current observations. I will rush through this, but the idea is the mystery is deepened because it's not easy to make supermassive black holes. As soon as you start making supermassive black holes by dumping tons of gas and material in it just to grow, what happens is it produces so much radiation that this radiation destroys the material flowing into the black hole. Just like radiation of the sun destroys a comet. Radiation comes, and because of radiation pressure, the material from the comet is blown away. It looks like a beautiful tail until at some point the whole comet is lost. Exactly that happens. That limit is called Eddington limit. And every time we try to build, using principles of physics, a supermassive black hole, it hits this Eddington limit and destroys itself. It cuts off its own supply of material. So we simply cannot form supermassive black holes in a very short amount of time. Okay, what deepens this mystery? This is how it is described in the paper that reported the discovery of UHZ1, that you simply do not have the time to create that black hole in the short time that you have available. In fact, the problem is the time is even shorter than the age of the universe, because some other people noted a beautiful thing, again using the principles of spectroscopy. They said that as soon as this black hole switches on and it produces this radiation, the radiation carves out a region which has conditions which prevent the absorption of radiation. Atoms are moved, things are done, so that again in that region which is affected by supermassive black hole, there is no absorption of light. This is called the proximity zone of a quasar or a supermassive black hole. This little part where you see, again, this is a spectrum. Most of the spectrum is gone, but there is this little bit where you see a lot of light shining through. And people said that because this proximity zone is created by the black hole, you can use measurements of the proximity zone to actually infer the age, how long this black hole has been shining. Isn't it remarkable that stupid idea about a spectrum from a prism you can use to actually measure the age of a supermassive black hole at the other end of the universe? And when you do that, you find that the age is very little. And so I think I really need to move on. But a brilliant student in my group who is now a postdoc in Spain, came up with a very interesting solution for this puzzle. I won't go into the detail, you can ask me, where she has come up with a way to grow these supermassive black holes which solve the problem. And of course, we have to now confirm that her picture is correct. So she has just received 384 hours on the James Webb Space Telescope to confirm whether his theory is correct or not. I will end my talk by talking about the third mystery. And the third mystery is what heated up the universe. Okay? This is the third mystery. Not many of you probably know what the temperature of the universe is, much less whether it's not what it's supposed to be. So let's quickly look at that. If I asked you, going back to this photo with which I started my talk, where most of this stuff is, you will of course say most of the gas in this picture is in the galaxies where we are seeing it. If you said that, you would be wrong. Most of the gas in this picture is actually in these dark spaces where you don't see it. 90% of the matter in this photo is not shining at all. It's located in these gaps between the galaxies. It is called the intergalactic medium. Most of the material of the universe is located in the intergalactic medium. Why are you not seeing it? Because it's really, really diffuse. If you take a cubic meter box in this room, it will have about 10 to the 1024 atoms, right? The Avogadro's number. It will have 1 with 24 zeros. Those many atoms would be in that box. Here, that same size box will have 1 atom. So it's that diffuse. And which is why it doesn't shine. But we know now how to see faint objects. We just have to take a spectrum. If you take a spectrum, hydrogen has a special line, just as the 21 centimeter line, called the Lyman alpha line. And that Lyman alpha line is suitable for this experiment. And you can see this. You can see this low density gas all the way. This is how we know that most of the matter in that photo is actually between the galaxies. You can take a spectrum and you can measure these atoms, spectral line by spectral line. I can tell you the temperature, the density, and the location of each cloud of hydrogen gas there. And when we do that, I told you, remember, that the spectroscopy can also tell me the temperature. I find that the gas is about 10 to the 4 Kelvin, 10,000 degrees Celsius or Kelvin doesn't really matter at that point, right? And so why is that a puzzle? Well, the puzzle is again because of the other end, we have extraordinary information here. And there we know that the temperature of the universe was about 1000 kelvins. And lambda CDM model, that beautiful edifice of human intellect, tells me immediately that if the universe's temperature was supposed to be 1000 Kelvin, it will be 2 Kelvin today. But this spectroscopy tells me that the temperature is 10 to the 4. What happened? In fact, if I keep doing this experiment backwards in time, again in the style of an archaeologist, I find that as far back as we can go, the temperature appears to be 10 to the 4 Kelvin. This process, which means at some point, again in that gap, unfortunately, this third thing must have happened, that somehow the universe was taken away from this lambda CDM curve and heated up. We don't know when this happened. We don't know what created it. This process we have given a name. We call it reionization. When the universe got heated up like this, I'll just tell you a story of how we actually learned in the last few years in my group on when this happened. We still haven't figured out what caused it, but I'll tell you the story of how this happened. It turns out that if I asked you to go backwards in time and try to find out when did reionization happen, you will say just keep doing your spectroscopy. Turns out you can't do it. About a billion-year mark, spectroscopy stops working. Okay, again, very unfortunate result. But then sometime back, somebody in California called George Becker pointed out that, yeah, your spectroscopy is gone, but I noticed something interesting, which is that the spectrum looks very different depending on where on the sky I look. Somehow, at that 1 billion year mark, my absorption spectra fluctuate a lot on point to point on the sky. Okay, what does that got to do with anything? Nobody knows. But I got curious, so I started imagining what could explain this. And one way to imagine this is to create computational models of imaginary scenarios for what reionizes the universe. So I imagined a scenario that at some point in that gap, new galaxies will have formed. Remember, galaxies have to form there. And I imagine that these galaxies are the first that produce UV photons. But I know that UV photons can ionize the hydrogen gas because they have very high energy. And as soon as that happens, it will turn the whole universe into a plasma that is hot. Completely imagined theory in my head. Okay, nobody has proved that it is correct. But as soon as a physicist has an imagined theory in his head, he can produce a calculation. And this is an example of the calculation in which slowly these galaxies are carving out regions in the universe which they are heating up. So that at the end, the whole universe has about 10 to the 4 Kelvin. Is this correct? It turned out that this exactly matched the data. In fact, I remember the morning, Saturday morning, 7:30, when I first realized that the model matches the data. And I learned that it only matches the data when reionization happens at a specific time. So it's clear that this really random scatter between sightline is telling me when reionization happened. Okay. In fact, this picture, at least it explains one observation, suggests that the universe should have evolved like this. Here on the x-axis is the time. The universe here was 650 million years old, and here about a billion years old. And what the top image shows is how hydrogen is being destroyed and ionized. The middle panel shows how the temperature of the universe is increased as a result from a few Kelvin to 10,000 Kelvin. And the bottom panel is showing how the radiation from these galaxies looks like. And you can see that the calculation this is a lambda CDM calculation, makes a very precise prediction for how the universe looks like. And it explains one measurement, sorry. You can ask, well, is this true? Is this how the universe looks like? We have actually made a lot of work on that. The first is we were given a lot of time on the world's biggest telescope called the Very Large Telescope, where we took many more spectra. These are some beautiful spectra that we took from 30 quasars. And using this, we have now confirmed that you need reionization to happen at that precise point to explain these observations. But further, we have been trying to think about whether we can actually see this structure whether we can actually see this happening in the real universe. And nobody knew really how to do it until recently. We have found that there is this remarkable class of galaxies which JWST is identifying sitting in the epoch of reionization, which have a bright spectral line at the Lyman alpha wavelength. And a brilliant postdoc in my group actually tried to study, Somak Maitra, who is here in the audience, he tried to study whether this Lyman alpha line can be used to actually reconstruct that patchiness of the intergalactic medium. Okay, because if the intergalactic medium in front of that galaxy is neutral, you shouldn't see that Lyman alpha line. It will be absorbed by the hydrogen. So the fact that you see it tells you something about how the gas is in front of the galaxy. And indeed, he has produced a beautiful algorithm which can take these galaxies and produce this beautiful patchy structure of the universe. So these galaxies which JWST sees allows us to measure the structure of the universe. This is a simulated image. I'm hoping that in a few years' time, we will have a real image to show you using this. So where we are, I posited three mysteries. When did the galaxies form? How did supermassive black holes form? And how did the universe heat up? I gave you our partial answers so far. We have figured out that the first galaxies can produce a detectable cosmic dawn signal, which we haven't detected yet in the 21 centimeter. But we think that that is the best way to find that point. We think that supermassive black holes must grow according to the model that Sindhu has developed. And finally, we have figured out when reionization ends, not much else yet. So what's next? The next point is, of course, we have to finish the job, right? We want to find cosmic dawn. We want to chart reionization, and we want to discover these first supermassive black holes to finally solve these three mysteries. I'll just show you roughly how this is going to be done in the last minute or so. The first is all of these calculations are enormously complex, and we do them on some of the biggest computers on the planet. So that is the one thing that we keep doing. But we will also use the biggest telescopes. So the James Webb Telescope, which is a beautiful American facility, is really remarkable. It costs $10 billion, but anybody can use it on the planet. We'll use telescopes such as REACH. There is a new telescope which I couldn't talk to you about today called the Square Kilometer Array, which 10 countries are trying to build to detect that 21 centimeter line. India is one of the countries. India has given about 125 crores to this project. There is this beautiful telescope called Rubin Observatory, which is a beautiful robotic telescope, which is just finished construction in South America. Again, TIFR has privileged access to this telescope, and we will be using this to address some of these puzzles. And ultimately, on the horizon, exciting is this engineering marvel called the extremely large telescopes. These are just the mirror is 30 meters in diameter. Just the construction of this is just mind-bending. And we are hoping that in about 10 years of time, we will have access to these new class of telescopes, which can just open new doors. So I want to actually end by making one point, which I don't see conveyed very often. Is well and fine to actually be very excited that there are these amazing things which these little scientists in Kulaba at Land's End are trying to figure out. But I want to give you a sense that this thing is not easy, and neither is it cheap. And I want you to carry back the idea that these galaxies are very, very expensive. This is very expensive stuff, okay? So big questions really need big answers. We are working really hard to unlock them, but these are not easy. These are all billion-dollar telescopes. Even just keeping these data on hard disks require hundreds of crores of rupees every month. This is all very expensive stuff, which is very ambitious, expensive, and long-term science. And I think one thought I want to share with you is that I think just as we support cricketers and artists and filmmakers, I think Prithvi Theatre is probably a very appropriate place to say this. And the reason we pay them crores of rupees is because we think that they enrich our lives by playing until 10:30 p.m. in Wankhede every summer. And I think I want to make a case that science is also a form of cultural enrichment. Okay, it's a very interesting idea that I want to carry and think about. And if you think about science as that way, science too needs support just as filmmakers and so on. So we need public and private funding to build new telescopes, create data centers and supercomputers, and train new PhD students and postdocs. But what we can assure in return is that we are doing these big things with really big ambition. In fact, when I get a bit philosophical in the mornings about cosmology, this is one of the phrases from my favorite poets that I like to hold in my mind. And I think I'll stop with that here.
Fantastic. Covering probably more than billions and billions years in 1 hour.
Yeah.
And I'm sure you must be having a lot of questions. But we'll take a tea break. We'll take a few online questions and take a tea break. You can come back and then you can ask all questions that you have in your mind. So I'm just reading a few online questions.
Yeah.
So how do you see Narlikar's steady state theory in the light of the experimental data and the other theories?
Yeah. So as far as we know, Narlikar's steady state theory doesn't seem to be consistent with our latest measurements. But I don't want to sound like um, um, the idea. So the question, more general question, is whether this lambda CDM model is confirmed. There are other models explaining the universe which are not lambda CDM. One of the famous ones, certainly in India, is Narlikar's steady state theory model. And the question can be asked whether that is consistent. The short answer is, as far as we know, it is not consistent with the data. One of the data sets where it really struggles with is the CMB. The steady state theory just cannot have the CMB. They can tweak the theory to somehow get something like CMB, but then the theory becomes a bit ugly and complex to survive as a valid theory. And then the debate gets a bit philosophical. What I will say, however, is that this is an active topic of research. There are wonderful cosmologists. I have not been working on that, who test the limits of lambda CDM. They try to ask, what if lambda CDM is wrong? And there is beautiful work being done on that. And those people do study questions about whether steady state theory has any hope. But I'm not really an expert on that.
So right now, lambda CDM is one of the forerunning model to explain.
By far, yeah. Lambda CDM, it's very hard to break lambda. If you break lambda CDM even by a tiny bit, you will be very famous in the cosmology community, or infamous, depending on how well you do it.
Okay. So the next another question is how exactly do the molecular clouds ionize, and is it possible to estimate the rate of ionization? What is the mechanism of ionization?
Yeah, this is a slightly technical question. The answer is the way the ionization is occurring is not that different from how light from this light is interacting with the molecules and atoms in the gas in this room when it reaches me. What happens is these photons strike these atoms, and then the atom responds to that in various ways. Again, it's a spectroscopic principle. If the photon has very high energy, there is a small probability that the photon will just knock out the electron from the hydrogen atom and dissociate it. How does this happen? How does a hydrogen atom sitting experiences a photon, and then suddenly there is no hydrogen atom, instead there is a free electron and proton? Is a topic that comes under a field of physics called quantum field theory, quantum electrodynamics. It is a beautiful theory in its own right, but it does happen. Okay, and then that is what happens in the universe at that point. The idea is, again, this is a hypothesis. We are still in the process of confirming this. Like the steady state theory, this is a hypothesis that these photons come from these stars. And the interesting thing is, the stars are the first things which produce these photons. There were none of these photons. So this tallies very nicely with the fact that reionization happens in the same period where the galaxies start. So there is as detectives call it, circumstantial evidence that this might be valid. So these high energy photons come, they hit these atoms, and then they knock out the electron. The second answer here was, can we measure the rate at which this is happening? Yeah, we can measure the rate. In fact, one of my figures showed that rate. It is totally possible to measure it, but how to do that is a technical detail that would be difficult to explain here.
All right. So let's thank Girish one more time.
Okay, great. Yeah, sister, I said.
He's the contact.